Hi everyone and welcome to this video on rules for differentiation. Now you're going to say, but didn't we do that in a previous video? Well yes, and that was differentiation from first principles. And you're going to go, from what? And I'm going to say from first principles. And that was tough. Well, more sort of long. I don't think it was particularly difficult, it was just finding gradients. But the point of it is there's a much quicker way. And lots of people, when they get to see this way, go, well, why didn't you teach me this first? And if you are taught by me, well, the good news is you've already been taught it first. But look, by the end of this video, you're going to know what the rule for differentiation is and how to find the rule, or how to find the gradient of a tangent at a point. Now, I'm going to circle this in red twice, in fact, because that's so important. Whenever you differentiate, remember you are finding the gradient of a tangent at a point. In fact, you're probably finding the function of the gradient of a tangent at a point. What does that mean? Well, basically, for any x value, if you know the equation, so for example, if you had y equals 3x minus 2, if I give you an x value, you're going to turn around and say, well, I can find a y value, because you just substitute it into that equation. Well, if I was to give you a gradient function and told you that for any x value on that graph, I can find the value of the gradient at that point, you'd be like, mind blown. That would just solve all of life's problems, wouldn't it? No, probably not. But it would be fairly important. So, previously we've looked at the ideas of constant rates of change, average rates of change, and all of this was just gradient, 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 gradient. We had curves where we drew points between, we had straight lines where we do gradients, or we did, the rise over run stuff. And all of this led to the same point, that eventually, whereas we're looking at the gradient between 2 points, the point of it is, the point, see what I did there? Point. Anyway, too many points. Is that I'm trying to get the gradient at just 1 point. 1 point on the graph. So if I had this graph here, and I had that 1 point there, what's the value of the gradient? Well, basically, this is what differentiation helps us do. Now, we always start with a basic rule, and I think it's a bit weird that we, go straight into some huge convoluted thing. But the rule is, when you have function of x, so for example, y equals x cubed. To differentiate it, what I do is firstly I write y dashed, and I'll come back to that in a moment as to why is it y dashed. But we multiply the power by the coefficient. Now I've not done a 0 there. The coefficient of that is actually 1. So you do the power times the coefficient, which in this case would be 3. You write the x and you take 1 from the power. So the basic rule is multiply the power and the coefficient and take 1 from the power. And that's actually pretty much it for differentiation. There's no more. Written more formally, you'll notice I've got this f dashed of x. Well, did you notice the little dash here? Yep. Well, when my equation is written as y equals, then we can express my differential function, and notice here, this 3x squared is a function, as y dashed. It's important to have the difference between the function and its differential. When I had f of x, we noticed the differential is expressed as f dashed of x. So because notation is one of those great things in mathematics, and we obviously try and throw 20 different ways of doing this at you, there are lots and lots of different ways of expressing differentials. F dashed of x, we've met that one, is the same as y dashed of x. And then this dy by dx business. Now that's actually called Liebnitz Notation. Why? I have no idea who Leibniz is. Maybe I can do a little bit of YouTubing and find out, or a little bit of Googling. But the point of it is, dy by dx basically means changing y with respect to a change in x. Now, realistically speaking, we should have delta y divided by delta x, because delta is just a little change. So we're looking at what happens with small changes in y, and that little divide sign we say is with respect to small changes in x. Because we don't want to keep writing these deltas, we actually write it more simply as dy by dx. So whenever you see any of these things, just know it means the same stuff. Likewise, we can express things in this way, that d by dx of my function of x is equal to f dashed of x. Now actually this is more important to us when we use my CAS calculator, because that's actually how pretty much most of the CASs set it out. So let's just use the examples on some basics. Now at the moment we've only got one example where we had y equals x cubed. But the good thing is we can actually daisy chain as many terms as we like. And when you differentiate each individual term. Now there are some provisos and buts and maybes and whatever else, but in this situation, in this example, this function, which is f of x, so I'm going to write f dash of x automatically because I'm going to do my differential function. And I'm going to look at each term individually. So 3x cubed, multiply the power by the coefficient, gives me 9x, and take 1 from the power. I'm going to add, well, 2 times 2 is 4x to the power of 1. Now, what is this minus, oh, itchy nose. What is this minus 5x business? What happens here? Well, whenever there is just a letter, we know that's the power of 1. So I'm going to do 1 times minus 5, which gives me minus 5. I'm going to write the x, and I'm going to take 1 off the power, which gives me to the power of 0. Now, 0, that was so much harder than it needed to be. And once again, look, every time I say 0, you get a mention. Say hello world. Hello world. Look at the camera. Say hi. This is 0. Yes, I know a maths teacher who's called his dog by 0. And as you can see, he's just adorable. But you really need to come quicker when I say 0. Now, say bye-bye world. Bye-bye world. And, oh, there we go. Back off we go down. Now, as we say, anything to the power of 0 is in fact 1. So that actually just becomes minus 5. And what of this plus 1 business? Well, I like to think of that as x to the power of 0 normally. So actually every single one of those terms has a power. In this situation, 1 times x to 0. Now when I do 0 times 1, what do I get? I get plus 0. And in fact, that disappears. Now, there are shortcuts here, and the more you do this, the more you'll actually find that any constant, 2, 3, 4, 107, whatever's on the end of this original function, will actually always will always differentiate out of this. It just doesn't exist. It's not there anymore. Anything with just a letter, so minus 5x, 10x, 127x, well, the x effectively disappears. Now, I don't like shortcuts because they get really messy. I always like to do things from first principles, but we now know that for this, f dash of x is 9x squared plus 4x minus 5. Yes. What about the next one? Getting harder? Probably not, just more of the same really. So what about this, how many terms I've got? 1, 2, 3, 4, 5 terms. They're giving me f of x, so I'm going to write f dash of x is given by, so multiply the power, which is 4 by 2, which is 8x, and take 1 off the power. Okay, I can do this. Minus 3 3s are 9x squared. 7 times 2 is 14, x to the power of 1. Do I need to write this power of 1? No, not really, so we can get rid of that. Minus 3. Now remember, 3x becomes just 3, and this last value here, which is the same as 8x to the power of 0, well, if I did 0 times 8, it disappears, and so that constant goes. Now, ask yourself the question, how would I now find the gradient at the point x equals 3? Well, if I wanted to find the gradient at the point x equals 3, I'm going to use my gradient function. And so what that's really saying is find f dashed where x equals 3. Well, okay, do you see that my equations are all in terms of x? Absolutely. And so what I'm doing is finding, by putting in 3 here, I get 8 times 3 cubed minus 9 times 3 squared plus 14 times 3 minus 3. Now I'm not going to work that out because I don't need to. But the point of it is I can now, for any single x value, for this original function here, I can find the actual value of the gradient at that point. Now, again, this one's really easy. I threw this in as a bit of a curveball, but 6x plus 3, well, 6x becomes 6, and thereby the gradient, or that last number, disappears. Now, a lot of people say, well, what does that f dash of x of 6 mean? Go back to my original function. If we look at this, what was it? Yep, it was a straight line. 6x plus 3, which means it's effectively going through there. It's going to go through plus 3, and it has a gradient of 6. And what did this tell me the gradient was? 6. How did I know the gradient was 6? Well, we've got here effectively y equals mx plus c. It's a straight line. So f of x is equal to 6x plus 3. My intercept was 3, and my gradient is 6. A lot of hard work for that. Now, as I said a moment ago, using differentiation to find the value of the gradient at a tangent at a point is really important. So when we differentiate, we're doing it for an actual reason. So let's jump into an absolute example, and it says find the value of the gradient. The minute I see the word gradient, my mind goes differentiate, differentiate, differentiate. To the point 1, 1. Now, whenever they give me a point, I know that secret code for an x value and a y value. And here is my function. They've called an equation. Here is my function. So find the value of the gradient. Right, first things first. I'm going to have f of x is equal to, and I'm going to just write the question out, 3x cubed plus 2x squared minus 5x plus 1. So I'm going to differentiate it. F dashed of x gives me, right, 9x squared, because I'm doing 3 times 3. Plus 2 times 2 is 4x minus 5. So my differential function is 9x squared plus 4x minus 5. And it says find the gradient at the point 1, 1. Well, it's telling me it wants it at the point where x equals 1. And good news, my equation has x's in it. So if I want to find the gradient when x equals 1, I do 9 times 1 squared plus 4 times 1 minus 5. Which gives me 9 plus 4 minus 5, which is basically 8. So the value of the gradient of the tangent at that point, so whatever this graph looks like, and wherever the x value was, let's say x value was 1, if I was to look at this point here where x equals 1, I would know the value of the gradient at that point would be positive 8, which would mean, yep, I've got a line, a tangent to the line with a gradient of 8. Now this is freaking awesome. Again, find the value of the gradient. Whoops, mind seeing gradient, and I'm like, whoop, 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 whoop. I'm going to differentiate of the tangent to the point 1, 9 for the equation f of x equals 6x plus 3. Right, so f of x is equal to 6x plus 3. F dashed of x is equal to, oh, hold on, I just meant this one, 6. Well, actually, although they've given me the point 1, 9, which is code for saying find the gradient when x equals 1, do you notice what's missing in my gradient function? Well, yeah, there's no x value. And if there's no x value, what that actually means is that my gradient all the way along that line is exactly the same. And we knew that because the line 6x plus 3 is actually a straight line, where the gradient at this point, and 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 in fact for all values of x, is exactly the same. 6. So a little bit of a trick question, but to me, the minute they use the word gradient, it's like, okay, I am going to differentiate. And the minute they give me a point, I know, you've given me my x value. Notice you don't need the y value, not for the differential. Now, as I said slightly earlier, we use different letters. In terms of dy by dx, we know is useful to us. It's a different way of writing stuff, but we don't have to use even y and x. What you can see here is you've got a formula that y equals 3t squared minus 2t plus 8. Well, that's useful because actually it's a constant acceleration formula, which we will come to in either physics or maths or whatever else. But in this situation, if I was going to differentiate this, I would write dy by dt. I wouldn't write x, I'd write dt. Why would I do this? Because my equation is in terms of y's and t's. So the y is on the top and the t is on the bottom. And in this situation, I would write 6t minus 2. Now, try not to get your x's and y's mixed up because it gets really, really complicated. Now, I love the CAS calculator. For those of you who are using the TI Inspire, really sorry, guys. I don't have screenshots at the moment for that. I'll add videos later on for how to use the TI Inspire. But I used to love TI Inspire. I used to think it was the bee's knees. And do bees even have knees? I don't like bees. Thank you very much. All right, but the point of it is, using a CAS is great. So this is for the Casio ClassPad, which I think is just an awesome piece of machinery now. If I want to do this on my Casio ClassPad, the first thing I do is I hit Math 2, and I go to that little box here in red, which has the D by D and a coloured in square and an open square. Now, obviously, it just means we're going to fill in the values. When my calculator comes up, it will ask me to fill in this little box here and this box here. You'll notice I'm putting x on the bottom because my equation is in terms of x, and then all I've done is type in my equation. When I hit enter, out comes my answer. All right, so absolutely freaking awesome. My calculator can do all of this for me. Interesting, I had a friend who used to know in Sydney who was very upset that Victorian students get to use a calculator to do this. I don't know what the rules are in the UK anymore, but I know part of me goes, yay, this is great, just to make this slightly smaller so that my head doesn't block this. Right, what do we see? We see finding the gradient at a point. Your calculator can do this for you. So, as an example, find the value of f dashed of 1. F dashed of 1 simply means differentiate, that's the f dashed, and then put the value of 1 as x into your calculator. And obviously we need a function, 3x cubed plus 2x squared minus 5x plus 1. So what do we do? Right, on the Casio ClassPad again. First things first, hit the interactive button, then calculation, and then diff. What does diff stand for? Differentiate. It comes up with the dialog box, and normally that first thing here is coloured in, but you don't want that first thing coloured in. You want the second thing, the derivative at a value. Now, derivative is another word for differentiation, right? It just wants the differential at a value. And you're going to say, well, yeah, I want to do it at x equals 1. So, expression, you type in your equation there, 3x cubed plus 2x squared minus 5x plus 1. You put in the variable. Now the variable just is like, well, what are you differentiating with? And in this case it's x. The order is always going to be 1, unless you're doing second order differential equations, and we won't even get into that. And the value is 1, because that's where we want to have this gradient. The gradient at x equals 1. Hit my button and out comes that expected value. Well, I mean, we already had it earlier, of 8. Nice and easy. Get your calculator to do the hard work. The CAS calculator is useful for so many things. What about finding x values on a graph where the gradient is equal to a certain value? Well, this is turning the question on its head. So you're not only being told to differentiate, you're being told to find the value of x given the gradient. You're not finding the gradient, you've been given the gradient. So this is one of those great situations where you're doing maths both forwards and backwards. So I've got my equation, standard now, 3x cubed plus 2x squared minus 5x plus 1. And I'm trying to find the gradient when x equals 8. So gradient, y dashed, is 9x squared plus 4x minus 5. Now I'm not putting x as 8. That's not what it's asking. It wants to know the value of x when the gradient is 8. And because I know that y dashed is the gradient, then I'm looking to solve the equation. 8 equals 9x squared plus 4x minus 5. Now your CAS can do all sorts of stuff, and I particularly like the define function. It makes life a lot easier for me. It allows the calculator to store a function. Then I don't have to keep typing it in over and over and over again. So first things first, we hit Math 3, then we hit the define key. Now this F and these brackets are really helpful because they already set up f of. Now we can put x's or numbers in any of these, and that's exactly what I've done. So I have done f, where it's given me a box, I put an x in there, I've put equals, and I've written all of my function, or typed all of my function in. What have I done then? Well, I have then said, right, now when I hit enter, up comes the word done. If it doesn't come up with done, you've made a mistake. The point of it is that done says, all right, I've stored it into your calculator. And now I can just say solve. Right? Your CAS calculator can do so much stuff, and solve is one of them. Solve, I've hit the dy by dx button, and it's done d, and it's put a square in there, so I've put an x, and then it's gone, what do you want me to differentiate? And I've said, well, f of x. Why f of x? Well, I've defined it. I've already told the calculator, let you remember that equation for this function. And I've put it equal to 8, because I've said solve, where the differential of my function is equal to 8, and I'm going to put a comma x, because you want to solve this equation for x. And lo and behold, out come two values. X is equal to 1, and x is minus 1.444. Reoccurring. Why are there two solutions? Well, this is a cubic. And as such, a cubic would generally, possibly, mainly, hopefully, have 2 points on there where the gradient is 8. There and maybe there. So those two values are really important to me. There is one other way of doing this, and it's the last way I'm going to show you on the CAS, and you should really try and practice this type of stuff. But again, find f dashed of 1, find the gradient when x equals 1 of the same function. Well, I've already defined it. You can see the word done there. I've already done solve. That's what we did before, but we can replace that now with d by d, and I'm going to put an x there. Once again, f of x. And what I'm going to do now is put a vertical line. So you can see on Math 3 is this vertical line, and then x equals 1. And what that says to your calculator is, differentiate my function and find the value when x equals 1. And I think that's so much quicker than keep typing in that function over and over and over again. So what have we done? We've talked about differentiation. We love differentiation. We've talked about the rules and why and gradients of tangents at a point, and I think I'm just about done. So, ladies and gentlemen, thank you so much for taking the time and watching. If you enjoyed it, why not subscribe? In fact, why not tell the world? Get out there and just say, hey guys, MaffsGuru, his videos are pretty awesome. Really appreciate it. Hit me up with a comment, let me know what you think, or watch another video. It's been great seeing you. Thanks very much for taking the time to watch. I'll see you again in our next video.